as we've gotten here to sample problem 17.9, I'm going to assume that you're fairly familiar with the steps that we use to solve these equilibrium problems. So I'm going to go through that very quickly. If not, you might want to back up and look at a few of the early problems if these steps are kind of going a little bit too quickly for you. So again, this is a type 2 problem. We're going to determine equilibrium concentrations when we're given initial concentrations and an equilibrium constant. So fuel engineers use the extent of the change from CO and H2O to CO2 and H2 to regulate the proportions of a synthetic fuel mixture. So we've got 0.250 moles of CO, 0.250 moles of H2O gases. We're putting them in a 125 milliliter flask at 900 Kelvin. And we'd like to know what the composition of the mixture is at equilibrium. At this temperature that they're telling us about, the Kc value, the equilibrium constant for this reaction, is 1.56. So going through the steps that we'd like to take, first step is always write a balanced chemical equation. So carbon monoxide gas plus H2O gas gives us CO2 gas plus H2 gas. First step. Second step, write the reaction quotient. QC equals CO2 times H2 over CO times H2O. Third step, make sure that the concentrations of materials are in the right units. We're talking about QC and Kc values, and again, they gave us Kc equal to 1.56, so we're going to have concentration units. So the concentration of CO, and again, this is initial, right? They tell us that we fill a flask with this, so this is an initial concentration. CO initially is equal to 0.250 moles, and we put that in a 125 milliliter flask, so that's 0.125 liters. That's 2.00 molar. It's actually going to end up being the same concentration for water because we have the same number of moles. So water, 0.250 moles. 0.125 liters, 2 molar. First step equation, second step reaction quotient, third step make sure that everything is in the right units, and fourth step is to use an ice table. So anytime we need to determine equilibrium concentrations, we're probably going to need an ice table. So let's set up our ice table here. We start out with 2 molar each of these. No product, so we don't need to do a Q versus K comparison because we know the only direction that our reaction can shift is to the right. We can't take away products that we don't have. Reaction coefficients are all 1 here, so these are all just X's. Sum these up. So the equilibrium concentration of carbon monoxide is 2 minus some amount. The equilibrium concentration of water is going to be 2 minus some amount. The equilibrium concentration of carbon dioxide is going to be that small amount, and that's going to be equal to the equilibrium concentration of hydrogen gas. So now they gave us Kc as 1.56, and we know that's equal to the equilibrium concentration of carbon dioxide times the equilibrium concentration of H2 over the equilibrium concentration of carbon monoxide times the equilibrium concentration of water. So these pieces all have to go in here. So this is equal to X times X over 2 minus X times 2 minus X. So here's where the flavor of these problems all gets a little bit different. The problem can get different in terms of how we can solve for X. I'll tell you that the quadratic equation will always work. You can get X squared, and then you can get X squared minus 4X plus 4, and you can get your quadratic equation to work here. But what's really nice is if you can find a simplifying way to do this. And with some of our other problems, I told you ways that we could have solving for x be simplified with one of our earlier problems here, right? Sample problem 17.7. Simplifying method is, well, we were given one equilibrium concentration, so we could use that to substitute in to solve for x. The simplifying method with this problem is what I call simplifying algebra. So what do I mean by that? Well, if we FOIL this out and have x squared over some terms down here that have x squared and x terms, there's no way to easily solve that without doing the quadratic equation. And that's kind of important to say here. If you have x squared and x and constant terms, the only way to really solve this is by doing quadratic. And that's messy and long. It's really great if we can just simplify it so we have either x or x squared terms. Okay, so what this means with this problem is it would be really nice if we could get rid of having squared and x terms. So watch this and see if this makes sense. Remembering that anytime we do something to one side of an equation, if we do it to the other, we maintain the equality. So I've got 1.56 equals x squared. Let me keep this as x times x here. X times x over 2 minus x times 2 minus x. I take the square root of both sides. I am maintaining the equality here. Okay? Maintaining the equality means that that's something I can do without changing the value here. Square root of 1.56 is 1.25. The square root of this here is x over 2 minus x. I've gotten rid of having x squared and x terms. Now this algebra becomes simple to solve, and x is equal to 1.11 molar. Once you figure out what your x is, then you need to substitute it back into what these equilibrium expressions were in order to solve for their actual value. So the concentration of CO2 at equilibrium is equal to x, which is equal to the concentration of H2 at equilibrium, and that's 1.11 molar. The concentration of CO at equilibrium is equal to 2 minus x, and again, that's equal to the concentration of H2O at equilibrium, and that's equal to 0.89. Now, one of the things that I'm going to tell you about with this problem is you have an easy internal check to see if you got the right answer. We can put these values back into this and make sure that we get 1.56. So again, Kc is equal to 1.56. If we have the right values here, we should be able to put in 1.11 and 1.11 over 0.89 and 0.89. We should be able to put that in and get 1.56. And indeed we do, so we know we got the right answers.